Hello and welcome to NPTEL MOOC on Fiber Optic Communication Systems and Techniques course. So far in the previous modules we have looked at light as a wave, we have also seen light as rays, we have looked at Snell's law of reflection and refraction, we have seen how to look at those Snell's laws from electromagnetic perspective, that is starting from Maxwell's equation, what should we infer about what happens when light is incident on a medium and undergoes total internal reflection. We have seen that there is a non-zero field outside the medium as well, that is the medium in the medium of the lower refractive index. So, with all the tools that we have developed in the previous modules, we are now ready to consider the basic problem of communicating information using light from one point to another point. Okay. You might feel that the simplest possible way of communicating information by light is to somehow get light to change its properties. So, maybe its amplitude can be changed, or maybe its frequency or its wavelength can be changed in response to whatever the information that you want to transmit, right. So, this information that you want to transmit is itself coming from a non-electrical type of a waveform to electrical waveforms, and these electrical waveforms will be further converted to optical waveforms. That is, that process of converting information in one domain to another information, or at least varying one of the properties of the other wave in response to a modulating or information wave, is called as modulation, right. So, this basic process in which I take information in say electrical form and convert it into optical form by varying one of the characteristics of light wave would be the modulation. So, once I have this information, I modulate the information onto the optical carrier, okay, which is essentially a light wave, and then you might think that the simplest way of conveying this light wave would be to just beam it across the communication point. So, for example, you might have played with torch lights when you were kids or maybe even now, and you would see that if you hold up a torch light onto a room which may be initially dark, then you see that the image of light, or rather light, actually passes through and illuminates the room. So, if this light itself would be changing, then there's corresponding changes would also be visible across the room, right. You might have seen laser pointers. So, instead of using a torch light, if you have used a laser pointer while making a presentation, for example, you might actually point out the laser onto the screen and then move it around. So, if you can somehow automate this process in which information would then change the laser characteristic, maybe that it is pointing or something else, then it is perhaps possible for us to directly convey this information. In fact, this approach of using light wave and communicating light wave directly to the receiver, okay, sometimes called as line of sight communication, is not altogether new, nor is it not used. Actually, it is quite gaining popularity in the recent years under the name of visible light communications, and there are various versions of visible light communications which make use of this fact that you can modulate a characteristic of light and then shine this light across directly to the receiver. Okay. The problem with this near field, the problem with this visible light communications is that it is mostly restricted to near field communication. So, you can't go long distances. For example, the distances that we talk about in optical fiber communication, which is across continents, you can't really reach that with shining a laser pointer or shining a torch light across over that. There are a lot of technical difficulties and there are a lot of communication channel difficulties as well. The channel is very lossy, cannot support high data rates, cannot allow multiplexing of various users unless they are spatially separated, and moreover line of sight communication is also not possible because of, or at least it is very difficult because of the diffraction nature of light. So, all these technical difficulties that exist both in terms of how to make the technology necessary for this type of long distance communication, plus overcoming the limitations of the channel itself because of all these properties, and the problem of light having light getting diffracted, means that this type of visible light communication is actually suitable over a distances of a few meters and not more than that. So, then it is simply not possible for us to do long distance communication with visible light communication, then what is our hope? Our hope in fact is not new, in fact it has been there since 1960s onwards, late 60s onwards, in the form of what is called as optical fibers. And I have shown you in the introduction class of this course how an optical fiber looks like. So, you have an optical fiber in the form of a round wire. It actually has multiple layers. There is a central layer called as core, then surrounding the core you have a cladding, and surrounding the cladding for mechanical purposes of giving it a certain strength and durability, then you have a coating, and after coating you have a jacket. And usually these fibers are not just given to you in the form of jacketed fibers, they are usually also for communication purposes, they are actually combined, multiple fibers are combined into cables, and these are the thick cables that actually are laid underground, mostly underground, sometimes overground as well as hanging cables, but that is very rare scenario, mostly underground cables, and there have been millions and millions of such fibers that have been laid, which today enables the high speed long distance optical communication systems. So, clearly the mode of communication is different. In the visible light communication, you would just take the light, shine it across, and then the receiver would capture a portion of it, and hopefully whatever the captured portion, that would be sufficient for it to decode the information, or rather demodulate the information. Whereas in the fiber based kind of a communication, you actually have a physical layer which communicates. So, from one point to another point, the communication is happening with the help of a physical media, which is the optical fiber. So, we have looked at one type of communication where distances are limited to about a few meters, which is the visible light communication, and we have also looked at or we have at least talked about the communication systems that are actually very long range, right. So, we have talked about optical fibers as communicating media or communication channels which cover distances across continents, across countries. There are other situations where it is necessary to guide light from one point to another point, okay, where the distances involved are just about a few tens of micrometers to about a few millimeters, or maybe few millimeters to about at most say about a few centimeters. What possible communication could happen in these small distances from a few microns or millimeters to a few centimeters? Such communication actually is necessary in what is called as integrated optical circuits. Okay. Integrated optics is essentially like an integrated electronics chip. Okay. So, you have an optical chip which would take light from its source, guide it, and then maybe modulate it, and then sometimes if it does not modulate, it may simply decide to split the light into 2-3 parts and then send them across. So, in all this light guiding, control and manipulation, the distances involved are not very large. So, we are going to look at those type of guiding mechanisms which we call as slab waveguides, okay. And these slab waveguides are the basic components of any integrated optical circuit. Okay. You might ask, why are we talking about slab waveguides when the distances involved are not very large? It turns out that slab waveguides, as I have told you, are very important for integrated optical circuit applications. Some of those slab waveguides will make an appearance when we discuss photodetectors and when we discuss lasers. But for now, the reason of introducing slab waveguides is because it provides us with the ideas that go behind or that are also applicable to an optical fiber. So, to understand light propagation in the optical fiber, we consider the simpler case, that of the slab waveguide. So, what exactly is a slab waveguide? Well, before we go to slab waveguide, let us look at what we have done in the last few modules. We had an interface which was separating two refractive indices N2 and N1, right, and we consider the case of N1 greater than N2. So, clearly what we are aiming for is some sort of a total internal reflection, right. So, I have an interface normal, okay, and then I send in light at a certain angle theta 1. Now, as long as the angle theta 1 is less than the critical angle, there is nothing specific going on about this particular system or this particular arrangement, but when angle theta 1 becomes greater than the critical angle of the interface, please remember that the critical angle of the interface is obtained by applying Snell's law. So, N1 sin theta IC must be equal to N2, okay, but of course from the wave theory point of view, you know that there are actually evanescent waves, and these evanescent waves decay perpendicular or along the normal to the interface, but they essentially propagate along the interface itself, right. So, we have seen this kind of a thing when we discussed total internal reflection. Now, what I have is I send in light, okay, at an angle theta 1, and at this point I do not concern myself with whether I am dealing with a transverse electric polarized wave or transverse magnetic polarized wave. So, I just have light. You can think of this as in the form of a ray or in the form of a wave. Okay. For now, we think of this in the form of a ray and do not worry particularly about whether it is TE or TM. What happens when theta 1 is greater than theta IC? You know very clearly that the light incident would actually get reflected back, right. So, this is the phenomenon of total internal reflection. Of course, from the wave theory point of view, you know that there will be an additional phase shift that this particular reflected light will experience, and this phase shift depends whether we are dealing with a TE or TM. That is the reason why I have not yet introduced the picture of this phase information over here and simply dealing with the ray kind of an approximation over there, over in this case. So, let us actually look at the importance of this scenario. By total internal reflection, okay, what we have done is to actually confine light entirely into this medium. So, if this medium goes off all the way to infinity, then light is confined in this medium, right. So, light has not penetrated or does not really exist in this lower refractive index medium. Of course, forget about the evanescent waves at this point, because in the ray picture there are no evanescent waves. The ray of light completely reflects back. But this really does not solve my problem. For example, let us say this is where I have kept my optical source. The only way I can communicate now is that if I keep a detector exactly at this particular angle, so that the ray of light gets reflected and whatever the information that you have that you want to transfer is now received, because information is riding on the light source. Unfortunately, if my receiver stands somewhere at this point, there is just no way, or at least it is not possible with this kind of a mechanism. I have to adjust the angle theta 1 to send light across this, and sometimes I might not even be able to do so, right. You might of course say that why do not I move the source up and then make it parallel to the detector, or like in the line of sight of detector, but this is simply the problem of VLC that we have been talking about, which is what we do not want to perform, right. So, what is the way out, right, and of course, there is another technological problem here. I mean, I cannot really have a medium of infinite refractive index, right. So, I have to have a finite medium. So, the solution for our problems is to actually put another interface, okay, and this interface in integrated optics is normally called as a cover. This is called as a film or sometimes called as a guide, and this one is called as a substrate. Okay. Here we have seen that the cover has a lower refractive index than the film layer, and in this particular substrate, if I were to have a refractive index which is greater than N1, that is of the film, then light when it is incident at this interface would then have partial reflection and partial transmission, and after a few such back and forth reflections, then the amplitude of light would actually go down to 0, because at every reflection it would start losing out light. Okay. To avoid that, the refractive index N3 of the substrate is also chosen to be less than N1. Okay. Usually the substrate is intermediate between film and the cover, that is film refractive index, which is N1, is greater than the substrate refractive index, which is N3, which is greater than the cover refractive index, which is N2. Such slabs, okay, the substrate need not be infinitely long, it may be terminated at this point, okay, and this is essentially like a slab that you are carrying around. So, you have if you want, you can imagine this to be your duster, okay, where you have a lower this one, and then there is a sponge on top of it which is used to erase erase the board, right. So, this is what we would call as the film. The cover in this case would be just air, and this would essentially be the substrate. The substrate should be sufficiently thick so that any evanescent rays, remember if I have the condition that N3 is less than N1 and the angle of incidence here is greater than the critical angle, then light will be totally internally reflected back into the film medium, leaving only the evanescent wave here. So, if your substrate is sufficiently thick such that the evanescent wave amplitude is almost gone to 0, then that essentially would have allowed you to confine light entirely into the film region. So, this is what is normally done. So, a few micron thickness of substrate which is usually larger than the film thickness is sufficient to confine light entirely into the film region. And because we considered 3 different layers, each of them having different refractive index, this is called as asymmetric slab waveguide. Okay. This is called as asymmetric slab waveguide. But what we will do is to actually consider the symmetric slab waveguide, in which I have the film of refractive index N1 and the cover and substrate both with of same material. Okay. So, this is called as symmetric slab waveguide. This is the reason I am doing this is just to kind of get some reasonable expressions. The analysis is not really difficult if you were to replace this symmetric slab waveguide with a asymmetric slab waveguide. Okay. So, what am I looking at here? So, I know that I need to incident light, right. Somehow I need to couple light into this film in such a way that the angle that it would make theta 1 has to be greater than the critical angle, and once I ensure that, then I know that the light that gets reflected off would also be making the same angle theta 1, and it would also make the same angle theta 1 with the lower interface as well, right. So, this would also be theta 1, and therefore, light would be reflected back from this. So, the net effect is that after a few zigzag reflections, right, the light would then arrive at the receiver. Please remember that although I have shown this symmetric waveguide to be this particular long, a few centimeters long, in an actual integrated optical circuit this will be very short. Okay. Moreover, it will not be just right like this, sometimes it might also be curved. Okay. But those are topics of integrated optics which we are not dealing with in this particular course. The idea that we have done is or discussed is that it is possible by use of total internal reflection to confine light entirely into the film region and then transmit information from one point, that is at one end of the waveguide to another end of the waveguide, simply by allowing light to have multiple refractions, right. So, multiple reflections, total internal reflections. Now, having looked at this, it is not really telling me more information. For example, what is the relationship between the slab thickness and what are the allowed values of theta 1, what happens if the slab thickness is made smaller, what happens if the refractive index difference between N1 and N2 is made larger or smaller, is it any useful to have a control over the refractive index profile. So, what happens if I change the refractive index profile itself? All this information is not available to us if we were to simply follow this so called ray approach. So, what we do is that we do a mixed approach. Okay. We will first look at what is called as transverse resonance condition, which is absolutely critical, that tells us what values of theta 1 are allowed for light to be guided from one point to another point. So, it is important enough that I actually mention this. This is called as transverse, right, resonance condition. I will come to this in a moment. Okay. What this transverse resonant condition does is to actually show that not all values of theta 1 are allowed, and in fact, if I were to fix the waveguide, the film thickness. So, let me pick the film thickness to be h. Okay. If I fix the film thickness h, then theta 1, h, refractive index N1 and N2 and the light wavelength lambda, all these quantities are related to each other. Okay. So, these are all quantities which are related to each other, as we will now see. Okay. Go back to our case and of course, before we go to the transverse resonant condition, there is one additional thing that we need to assume here or consider here, that we need to consider whether we are dealing with a TE or TM. For simplicity, I am going to consider TE case. I am assuming that the light propagating inside the film is that of transverse electric polarized, is a wave which is transverse electric polarized, and therefore, the allowed values of theta 1 which are called as modes, or the allowed guided modes, are called as TE modes of propagation. A precise definition of modes and the concept of modes will appear in the not the next module, but the module after that. So, for now we simply think of mode as allowed values of theta 1. So, it is important, not every value of theta 1 greater than theta critical angle will be allowed to propagate. There is a certain condition that you need to satisfy, and that condition is the transverse resonant condition. Okay. What is transverse resonant condition? Now, imagine that you started off at some point here. Okay. So, this is the point which I have been marking, let me call that point as A, right. I know that this is the this is the k vector, right. This is the electric field or the magnetic field. In this particular case, this would be the magnetic field, and of course, the electric field would be perpendicular to this interface and pointing along the y direction, right. That is why we have considered the case of TE in this one. So, as the TE light is incident and gets reflected, you may now think of this case. So, as the light leaves this interface at at the plane z equal to A, and then starts to propagate along the green arrowed direction that I have shown, reaches point B and then goes back again to point again to the plane which is at z equal to C, right. What it has done is, it has done one complete round trip propagation, right. So, you started off with the plane at A, so you followed from A to B, and from B to C plane when you came back, you have actually traversed one round trip. Okay. What we now say is that in this traversal, if the overall phase shift in the direction perpendicular to the film, that is along the x direction for example. So, this is conventionally taken to be the z direction, this is conventionally taken to be the x direction for the slab waveguide. So, if the total phase shift along the x direction happens to be an integral multiple of 2 pi, okay, then the field at this point would be in phase with the field, that is field at point C would be in phase with the field at point A, and then this wave can then further undergo further reflections and sustain itself or be guided from one point to another point. Okay. So, this transverse resonant condition is the condition on the total phase shift along the x direction. Where is that coming from? Well, let us look at this one, right. So, we considered that this is a TE wave, and we know that for the TE wave the refractive index can be written as, or the reflection coefficient I am sorry, gamma TE can be written as n1 cos theta 1 minus n2, I think this is cos theta 2 divided by n1 cos theta 1 plus n2 cos theta 2. Please remember that theta 1 is already greater than critical angle, which means that cos theta 2 is going to be imaginary component. We have seen this one. In fact, cos theta 2 will be equal to square root of n1 square sin square theta 1 divided by n2 square minus 1 with a plus j, right, with a minus j because of the appropriate evanescent wave condition that we have described. Okay. So, what we have seen from earlier TE case or TM case discussion, not really TE case, but TM case discussion, is that when there is total internal reflection, the reflection coefficient can be expressed in terms of its magnitude and the phase, okay, which we will call as 2 phi TE, okay, because there is a complex number in the numerator, there will be a complex number in the denominator, and the magnitude of these complex numbers are equal, but their angles are opposite. Okay. And the magnitude of course turns out to be unity of whatever gamma TE that we have, this is actually equal to 1. So, that is the phase shift that I was actually talking about. So, as the ray of light leaves from the top at the plane z equal to A, arrives at B and then gets reflected back onto the film itself, there is a phase shift that it will undergo, and this phase shift is 2 phi TE. So, I had given this as an exercise for you to find out what is phi TE, and in fact, this phi TE is given by tan inverse of gamma divided by kappa f, okay, where gamma is equal to square root of beta square minus k0 square n2 square, beta itself is equal to k0 n1 sin theta 1 and kappa f is equal to k0 n1 cos theta 1. So, where are these beta, kappa and gamma coming from? Well, you look at the film case. So, this is the k vector, right. So, this k vector can be written as k vector will be this is directed along minus x direction and plus z direction, right. So, along the z direction the value of this wave vector will be z hat k0 sin theta 1 and along x this is minus x hat k0 cos theta 1, and we have simply labeled this k0 cos theta 1 as kappa f, and we call this kappa f as the transverse wave number, okay, and we call this k0 sin theta 1 as the propagation vector beta, or sometimes called as longitudinal propagation vector. Okay. So, this is what I have, and I have used these definitions and also written, instead of alpha in the previous module, I have written this as gamma, okay, gamma being the decay constant of the evanescent mode or evanescent wave outside the interface. And of course, you can also show that tan of theta 1 will be equal to the ratio of beta over kappa f, and you can also show that beta square plus kappa f square must be equal to k0 square n1 square. So, we know all this. If you do not know this one, then please know this one. So, these are some simplified notations that I am using to denote these expressions. Okay. What is important for you to understand at this point is that as the ray of light leaves the plane z equal to a, arrives at b, it undergoes a certain phase shift, and this phase shift in turn depends on the refractive index as well as the angle of incidence, and of course, what wavelength light is travelling, okay, and that is what is given by this expression. Okay. So, this total phase shift upon reflection is 2 times the value that I have shown here, okay, 2 times the value here, and when this ray now leaves B and arrives at the plane C, it undergoes another reflection, and reflection means it picks up an additional phase which would be 2 phi Te, right. And what is a transverse resonance condition? We have had 2 phase shifts, okay, one upon reflection here at the lower interface, one upon reflection at the top interface, but there is also a phase shift that you would have seen along the x direction, right. The corresponding component along the x direction would be kappa f, and because the distance or the height of the film is h, the resonance or sorry the phase shift here would be kappa f times h, and this phase shift here would be additional kappa f times h, and it turns out that if you add up all the phase shifts, okay, the phase shift upon reflection is actually because kappa f h and 2 phi Te are in opposite signs when it goes to the expressions, right. So, the transverse resonant condition will be 2 kappa f h minus 4, total phase shift was phi Te is equal to 2 nu pi, nu being an integer. So, this is a transverse resonance condition which we will discuss in the next module, the importance of this as well as how this can be used to understand guided light guided propagation inside the slab waveguides. Thank you very much.